Good morning, everybody. Hope you're having a great day. Today, we've got Codeforces round 725. Now, this is a Div 3 round, so in that sense, it should be a little bit easier. But it's also a 2-hour contest, and we're doing it with about an hour of time. So this should be fun. Many of you may be wondering, David, why are you only doing an hour of time? And that is, of course, because I'm looking for a challenge here. It has nothing to do with the fact that I was working on something until 3:30 a.m. It's totally because this is fully intended, and I've just been sitting here for the past 55 minutes twiddling my thumbs. So let's go. We're going to jump right into it, and we're going to be using Java for this. I'm going to be doing all of my solutions in contest, and it's possible to solve in 32 minutes. Of course, I am no Neil, so whether I solve it in 32 minutes is an entirely different story. I'd like to congratulate Galen Collin for doing it, I guess, in 33 minutes. So very good job to you, sir. And we're gonna see if we can keep up with that, or at least come somewhere close. At the end of contest, I'll have solutions to all of the problems I know how to solve, which is probably all of them. But really, what's going to be the main concern here is whether we get tripped up on something easy. Okay, so we're going to create our problem A here, and let's start. All right, Polycarp is playing a new computer game. It's got n stones in a row, and the stone in position I has power AI. The powers of each of the stones are different. Each turn, you can destroy the stone in the first position or the last position. Now, he wants 2 achievements. He gets them if he destroys the stone with the least power and the stone with the greatest power. What's the minimum number of moves you should make to achieve this goal? So there are 2 stones you need to destroy. In this case, these 2. And you want to know what's the fewest number of moves to destroy them. Okay. So you've got a couple options. You can destroy them both from the left, you can destroy them both from the right, or you can destroy one from the left, one from the right. And there you go. So, okay, hello. So we'll read in N, and then we'll read in A. And then we want to find the index of the smallest and biggest stone. So if A at I is equal to 1, then I1 equals I. Else, if A at I is equal to, well, can N be 1? No, it can't. So it's fine. If this is equal to N, then I2 equals I. Okay, so if I1 is greater than I2, then temp equals I1 equals I2 equals temp. So we'll swap them. And then otherwise, we've got 3 answers. So int ans equals math.min of I2 or math.min of, I guess this would be I2 plus 1. We would remove them from the left. Or we could remove n minus I1. That's how many things you'd remove from the right. Or you could remove I1 plus 1 plus n minus I2. Those are your 3 options, and then we'll print that. Let's verify that actually works. Uh, 24532 looks good. All right, on to problem B. Friends and candies. Very fun, very fun. You've got n friends. The ith friend has AI candies. Polycarp's friends do not like when they have different numbers of candies. Okay, we got it. Nice. In other words, They want all AI to be the same. To solve this, Polycarp performs the following set of actions exactly once. Choose k arbitrary friends and distribute distribute the candies they have among all n friends. During each distribution, during the distribution for each candy, you choose the new owner, which can be any of the n friends. Note that any candy can be given to the person who has owned that candy before in the distribution process. This is a very oddly worded sentence with the commas, but that's fine. Note that the number k is not fixed in advance and can be arbitrary. Your task is to find the minimum value of k. What are you trying to do? You want everyone to have the same number of candies. Oh, you perform this operation once. So how many things do not have the right number of candies? Or it's impossible. In this case, everyone needs to have, so what's the sum? 10 plus, so the sum is 16, so everyone needs to have 4, so you need to choose 3. Oh, you need to choose 2, because there are 2 things with more than that. All right, sounds good. Yep, let's do this. So first, we need to read in n, and then we need to read in a. And then we need a long sum equals 0. So sum will just be the sum of elements. And then if sum modulo n is not equal to 0, print -1 and continue. Otherwise, it is equal to 0, so then everyone needs to have n elements, or sum over n elements. So now everyone needs to have some elements. So now we need to count how many are bigger than this. Oh, I'm sorry. This has been really small for you guys. My bad. My bad. So we need to print how many are bigger than this. So if I is greater than sum, and count plus plus. Let's just run this real quick. Looks good. All right, on to problem C. You're given an array of n integers. Find the number of pairs where the sum ai plus aj is greater than or equal to L and less than or equal to R. All right, we got B. Nice. Okay. So we can just, for each L, find the L and the R that work with binary search. Are the numbers distinct? If we had, there's a tree set which is like number less than or equal to, which would be amazing, but this is fine. Oh, I has to be less than j. Yeah, man, if we had the number less than, that would be really terrific, wouldn't it? Well, we can do segment tree with lazy propagation. I guess we'll do implicit segment tree for this then. Okay. So we need a segment tree node with a left child and a right child, and a count. Public st. So in the constructor, we need to pass in this. Okay, so then to update something, we'll update into I, count plus plus. This isn't static, and then if this is a root node, then return, because we don't have any children. Otherwise, if lchild is equal to null, then we want to make kids. mid will be leftmost plus rightmost over 2. L child equals new seg tree from leftmost to mid, and then R child equals new seg tree from mid plus 1 to rightmost. Okay, so then we will make our kids here, and then we need to say, yeah, this problem is way easier in C++ because there's just a structure that does this whole thing for you. But if I is less than or equal to L child at rightmost, then L child dot update I, otherwise R child dot update I. Okay, and then what else? We need int range sum. Int L to R. If L is less than or equal to leftmost, and R is greater than or equal to rightmost, return sum or return count. If L is greater than rightmost, or R is less than leftmost, then return 0. Otherwise, we'll make kids, and then return L child dot range sum plus R child dot range sum. Okay, very good. So we need int n equals this, L equals this, R equals this. And then we're going to read in the array. From 1 to 10 to the 9, so this goes from 0 to the 9. Then for, okay, so we'll brute force R. Then I has to be less than J. Okay. So we want to this, print the answer. Okay, so now we need to update and then update. So st.update a at p2. Excuse me. So the minimum will be L minus A at P2, and the max will be L, or it'll be R minus A at P2. And then ans plus equals st dot range sum from min to max. Let's make sure this works here. 2701 looks good. Oh, print writer, I think. No, probably not, actually. Because we probably don't print that many things. Yeah, 10 of the 4 test cases. All right, we'll move on and then come back to that later if we get it wrong. So, whoa, F has lots of solves. So we're gonna do F. You're given 2 integers, L and R, where L is less than or equal to R. L is less than R, sorry. We want to add 1 to L until its result is equal to R. Thus, there will be exactly R TLE for real. Okay, we can update this later, but that's annoying. We'll add 1 to L until its result is equal to R. Thus, there will be R minus L additions performed. For each addition, let's look at the number of digits that will be changed after it. So you change 2 additions from this to this, or you change 2 digits. You change 2 digits from 9 to 10. You change these 5. Yeah, okay. I'll put the total number of digits changed if you want to get R from L, adding 1 each time. So we can store the total number of digits changed to get to some number, right? So 20, this will change 2 times, and then this will change 2 times 10 times. Plus 0 times. And then if we know the number of digits to get to 10 and the number to 20, it's just a subtraction of them. Yeah, okay. So we'll have L equals this and R equals this. And then the answer will be count R minus count L. So this is the total number of digit changes to get from 0 to X. Okay. So for char C in X plus this dot to char array. So we want int num ways equals 1, I guess. Well equals 0. So in this case, ants plus equals C times, or C minus 0 plus ways to get here. And then ways to get here times equals 10, I think. Is this right? I'm not really sure, but we can just test it. Nine. Well, what is 9? What is 10? 1. Ways to get here plus equals this thing. Eight. Okay, this should be 2. And then 8 to 11, no. Oh. Do we only want this? All right, good enough for me. Sounds good. Okay. So we should go solve something else. We got that. Yeah, let's read D and then we'll come back to C in a minute. You're given two integers a and b. In one turn, you can do one of the following operations. Take an integer c and divide a by c. Take an integer c and divide b by c. Your goal is to make a and b equal using exactly k turns. You can make them both equal to 1 always. What if k is equal to 1? Okay. So if k is equal to 1, we use special case. If it's not, we just need the total number of factors. Yeah, okay. Sounds good. So we need a, b, and k. We also need count factors. Oh, are we going to have time limit issues? We are we? Square root of 10 to the 9 times 10 to the 4. Well, okay, so if k is equal to 1, if a mod b equals 0, or b mod a equals 0, then sys out yes, else sys out no, continue. There might be time limit issues here. I don't know, I guess I can try it. Oh wait, what do we want? We want prime factors. Well, I guess we'll just use polar draw, huh? What? Oh boy. Okay. Alright, so now int max moves equals get prime factors. A dot size plus get prime factors B dot size. Okay, so if max moves less than k, so no, else is out yes. Oh. So we'll see about the runtime there. Polared row might be the tricky part, but should probably be fine. TLE, okay. Alright, so 4 equals 0, or equals, well, alright, so now for I in primes. If x mod I is equal to 0, count plus plus, while x mod I is equal to 0. Oh, and then if x greater than or equal to 1, plus plus. See if this passes. Otherwise, I guess we just need print writer, huh? Yeah. Okay, that's fine. All right. Let's read E. Funny substrings. Polycarp came up with a new language. You have two types of statements. X equals X. Or X equals A plus B. Alright, so, yeah. So what we can do is we can build a tree out of each of these statements. Where each thing goes to like the previous link. Or I guess we can just manually do it naively. So we need to store how much of haha does it start with, how much of haha does it end with, or I guess what are the first one, two, three. Okay, yeah. So what are the first three characters? What are the last three characters? How many ha-has are in the middle? Yeah, okay. So this is problem E. So we'll need some static class res, long n times in middle, k of c1, c2, c3, well, k array first 3, k array last 2. And then we'll need some static res combine. The res first, res last. And then we'll also need an int length, I guess, or a long length. So public res first, res last. Okay, so now long times equals first dot n times plus last dot n times if first dot last 3 at offset equals h, and first dot last, I guess this is okay. So if a at 0 equals h, and a at 1 equals a, and a at 2 equals h, and b at 1, or b at 0 equals a, then times plus plus. Okay, now we need 1, 2, b at 0, and then b at 1. And then we need 2, b at 0, b at 1, and b at 2. Okay, so then this dot length equals first dot length plus last dot length. This dot first 3 equals first dot first 3. This dot last 3 equals last dot last 3. This dot n times in middle equals times. So now we can combine two things that are of length at least 3. Still have this h problem though. So we can reuse this logic for both. We can reuse the length for both. The problem is this first 3 and last 3 is a bit sketchy. So okay, so if this is the case, All right. First at character is less than 3, int I equals 0, I is less than first at length, I plus plus, then known dot add first dot last 3 at I. Else for char C in first dot first 3, known dot add C, and then same thing in the last 3. First 3 at 2 equals last 3 at 0 equals known dot get I. First 3 at 2 equals last 3 at 1 equals this. Otherwise, all right, cool. Yes. Okay. So then we have a int n lines equals this. Okay, variable names can be multiple characters, looks like. Yeah. Okay, so we need a hash map string to res. Hash map string var equals this. String query type equals this, query type dot equals an equal sign. Then this is addition, otherwise this is assignment. Okay, so what do we do if it's assignment? So now string target equals next. res r equals new res equals a, then count is plus, and then return count. So int in middle times equals count times target. Int len equals target dot length. Target, or we need in middle times something something and then length. All right. Okay, let's go. Come on, what's wrong with this? Why we have another I? Okay. So we have this, that's fine. What if length equals 1? Then first 3 at 0 at 2 equals last 3 at 0 equals target at 0. Okay. All right, and then map.put there are, in this case, we need res l equals map.get this, res r equals map.get this, and then map.put there new res lr. Res last equals null. Last equals this, and then last equals this. Oh, so there should be 2. Yep. 1. Oh, darn it. Okay. So raise dot, how much time do we have here? 15 minutes. Where did that come from? Okay, so is this wrong? Oh wait, so the first three, we want to be right aligned. No, first three we want to be left aligned. Okay. Okay. Let's read G. And I guess we just won't solve C. Oh, wrong answer, really? Alright, well, we'll just solve this last one then, and then go through solutions. Polycarp has X red and Y blue candies. Using them, he wants to make gift sets. Each gift set contains either A red candies and B blue candies, or vice versa. Any candy can belong to at most one gift set. Help Polycarp find the largest number of gift sets he can make. What? Okay. In the first set, there will be this many red, this many blue. In the second set, there will be the other. Yeah, so we delete 2 each time, and then we take 3 from the bigger. Alright, so we've got some fixing up to do here. In 5 minutes of that. Yeah, I don't know. Oh, this is wrong. Really? Known dot size minus 3 plus I. Oh. Well. Yeah, so I think that's E. Alright. So I guess we'll go over solutions now, real quick. There are going to be some speedy solutions, though, because I have a meeting in 10 minutes, I think. So, yeah, speedy solution time. Yeah, so we just got that. Alright, so here is the idea for each of the problems. For problem A, you just want to know the position of the value of 1 and the position of the value of n. So if you're looking for a 1, right, you just find where the 1 is in the array, find where the n is in the array. There are a couple ways of doing it, but basically you either need to, in this first case, you need to delete some prefix. So you need to delete up until whichever one of them is later. Another option is you could delete some suffix. You could delete up until whichever one of them is earlier. And the last way of doing it is you could delete some prefix and some suffix, right? So delete everything up to the whichever one is first, the 1 or the 8, and then delete everything up to whichever one's last, the 8 or the 1. What that looks like is this. So we have the index of the first one and the second one, and then we make whichever one comes first be I1, and the whichever one comes second is I2. So your choices are, you take 0 up until the second one, I2. So that's index I2 plus 1, since this is 0 based. You take everything from the end all the way up to I1, which is n minus I1, if these are 0 based. Or you take the prefix to I1 and then the suffix from I2. Those are your three options. Whichever one deletes the fewest moves is how you do it. Okay, that's problem A. For problem B, yeah, so for problem B, you want to distribute these candies evenly. So in this example, you know there are 16 candies total, and there are 4 people. So if they're distributed evenly, each person gets 4 candies. And if everyone's going to wind up with 4 candies, then what you can just do is take from all the people who have more than 4 candies and then give those out evenly to the people who need them. The way you do that is you would start by giving to the person with the fewest number of candies, and you keep doing that until everyone has 4. So that's the idea. It's pretty easy. It's pretty easy to prove if you want to. But basically, you just need to say how many candies will each person end up with, and then how many people have more than that, and that's your answer. So very easy to implement. Count the sum. If the sum isn't divisible by n, then people can't end up with the same number of candies, so it's impossible. Otherwise, you count how many people have more than that initially. And they have to give at least one of their candies away. All right, problem C, number of pairs. So this is a pretty easy problem. I just didn't have time to finish it. But the idea behind it is you just want to say how many numbers are in some range. In C++, you've got this tool called like an ordered set, where you can see how many elements in some tree map are less than some element. And that's exactly what you're looking for here. But alternatively, you can use a segment tree or a Fenwick tree, and that can give you the answer for this problem. Yeah, so what's the idea here? So you can increment like one of the pointers, and then for the other pointers you have some set of numbers, some multi-set, and you need to see how many are in some range. In particular, right, so you need the sum of these two elements to be between L and R. If AI is 7, then you need AJ to be between L minus 7 and R minus 7. So you need to say how many elements are in this range. What I tried to do was use this thing called an implicit segment tree for this problem, and it kind of worked, but it also kind of didn't, so it kind of TLE'd. And maybe part of that was because of, I'm calling this make kids in the range sum method. Yeah, not totally sure about that, but that's the idea. You can do it with an implicit segment tree. You can also pre-compute which elements you end up updating, right? So you know this is going to be an element in the array, and then you can coordinate compress these and then use a Fenwick tree to do this faster, and that would improve your overhead. So that's one way of speeding this up to be faster than what I wrote here, and that would end up being right and probably pass within the time limit. So yeah, that's the idea there. Okay, that's problem C. Let's talk about problem D real quick. D was a bit easier, I thought. So it's a problem about finding divisors. You have two integers, a and b, and you want to make them equal in exactly k steps, where each step is dividing some by one of their factors. So the first thing to notice is it's always possible to do in 2 moves, right? You can make a equal to 1, and then you can make b equal to 1. That works. So if the number of turns is 2 or more, you just need to say, can you get to 1? Can you make both of them equal to 1 in this many moves total? We'll talk about that in just a minute. If k is equal to 1, then you have to divide some number out of the other to make them equal, right? So that means they can't start out being equal, because you have to change one of them. And also, one of them has to be a factor of the other. That's pretty easy. Okay, so we've handled the k equals 1 case. When k isn't equal to 1, we have to say how many prime factors are there total. Because each time you do this, you'll remove one prime factor from one of the two numbers. At least, you may remove multiple prime factors. So you just need to know how many prime factors are there total in both of the two numbers. You can do this pretty easily. It turns out that it passes if you just iterate through all primes all the way up to the square root of 10 to the 9. And then you know a number can have at most one prime factor bigger than its square root, right? If it has 2 prime factors bigger than the square root, when you multiply those together, it'll be bigger than that number. So that's not possible. So you can have at most 1 prime factor bigger than your square root. And then you can check for all of the numbers smaller than your square root, how many times that number is a prime factor, and divide it out. So you can find everything smaller than the square root of some number. You may or may not have an element bigger than your square root, right? So like the number 12 all of its prime factors are less than the square root of 12. But for the number 17, it has no prime factors less than its square root, and then has one prime bigger than its square root, which is 17. So you can get rid of all the small stuff and then be left with the one big prime factor. So that's the idea. So to count them, don't worry about this. I store a list of all of the primes up to some small value, and then I say, well, this prime factor divides it, then add 1 to the count of the total number of prime factors that x had initially, and then divide it out. And then finally at the end, we might have one big prime factor left over. So yeah, that's the solution. I also do this prime sieve right in the beginning to find all of the prime numbers up to 40,000. And the reason I chose 40,000 is because that is about the square root of 10 to the 9. So 40,000 squared is about 10 to the 9. Okay, that's problem D. Problem E, well, I guess let's talk about problem F next because it had quite a bit of solves. So for problem F, what we can do is just store, we want to see if you go from L to R, how many digits change total. What we can do is just see if you go from 0 to some number, how many digits change. And then what's going to happen is basically you can imagine a counter going from 0 to L, and then all of those are free, right? You'll subtract them out later, and then go from L to R, and those you don't subtract out. So basically, we'll make this problem a little bit easier and say how many digits change if you go from 0 to some constant. So yeah, that's the problem. What we can do is look at each digit and say how many times does this digit change. So it's not too bad actually, but basically what we can say is, like, for this digit, if this is a 6, right, then the last time it goes from 0 to 6, it'll change those 6 times. But also, every number in the prefix will cause this to change some number of times too, right? So if we have a 1, 6, then for that 1, each time that 1 goes from 0 to 1, this 6 will change 10 times. And then for anything else in the prefix, anytime that changes by 1, this 6 will change 10 times. So we can store for the prefix what's the value of the prefix before some number, right? So like for what's the value of these numbers. And then we can also store how many times does this number change. The loop for that looks kind of like this. Excuse me. So ways to get here is how many ways can we get to this number, right? Like in other words, how many times does the prefix require this number to change? Initially it's 0, and the only reason this number will change is to increase itself. But later on, numbers before this will force this number to do cycles all the way up to 9, and then back to 0, and then up to 9 again, etc. So 10 changes per cycle, I guess. Yeah, and then this is what the for loop looks like. So we go through each digit. The stuff before us, when we process a new digit, that'll get pushed over by 1. So we need to multiply it by 10 to move it over by 1 here. And then we need to increment this digit all the way up to what it is. So if this is a 6, this digit needs to get changed 6 times in order to move it to 6. And then we need to say for future digits, this needs to become a 6, so those will need to go from 0 to 9 another 6 times. So that's what this is doing here. I guess to reiterate, the general idea behind this problem is we're going to count how many digit changes will happen if we have a scoreboard go from 0 to x, right? That's what we're trying to count. And then we can do that by looking at each digit, and then for some digit, we know it'll change from 0 to x, but we also know everything to the left will cause it to do a cycle. So that's what this logic is doing here. The final solution here, I can't say that. The final main method of this problem, oh man, that's gonna get, oops. The final main method of this problem is going to be you count from 0 to r, and then you count from 0 to l. The stuff from 0 to L is free. Stuff from L to R you have to pay for. Okay, that's problem F. What do we have left? We have E and G. Okay, let's do those real quick. E is kind of annoying, but not too bad. So you have this language where there are two things you can do. You can assign a string to a variable, or you can concatenate two variables together and put that in some other variable, or maybe one of the same variables. So what you can do is just do these two things, and then you want to see at the end of the process how many times does the string haha appear. There are a lot of things, there's a lot of data here, so you can't actually simulate it, but the key observation is that there isn't actually that much that you care about. In particular, all you care about is what are the first three letters of some string, what are the last three letters, and within the string, how many times does haha appear? Because once you have some really long string, the stuff in the middle will never be affected. So you just care about the small prefix and small suffix, and then you care about within the middle, how many times does this haha appear? You can actually maintain those things, right? So since all you're doing with these results is concatenating them together, the total number of hahas that appear will just be the number in the prefix, the number in the suffix, and then also how many overlap that border, which is why you need to store the prefix and suffix of 3 characters for the 2 halves, right? So you need first half, second half, and then the stuff that overlaps the middle. Yeah, so this is really just a lot of annoying implementation that you have to be careful with. I made this result class, and for me what it stores is how many times does a haha appear in the middle, what are the first 3 and last 3 characters, and then what's the length. I use this length just because when things are fewer than 3 characters, you have to be careful because the first 3 and last 3 characters will overlap, and they might not be 3 long. So yeah, this is generally what that part looks like. This is like counting the overlap. There are 3 possible ways it can overlap at the 3 cut points of haha, right? After the first character, after the second, or after the third. You can't overlap after the fourth because then the entire thing would be all in the first half. So yeah, these are the overlaps which we might need to count. And then other than that, we just need to maintain the first 3 and last 3 characters. To do this, what I do is I say, okay, let's get all of the characters we know of in the first one, all of the characters we know of in the second one, and then take the first 3 from those and last 3 from those, which might be a bit messy. I don't know. There you go. There's probably a cleaner way of doing this, but yeah, this way works at least. Yeah, so that's the idea. Most of this is just be careful. Just like be very careful with your implementation. Don't mess stuff up. Cool. The last problem is problem G, which isn't actually too difficult. I just ran out of time and wasn't able to finish. So yeah, the idea behind this problem is you have 2 gift sets A and B, and then you have 2 sizes A and B, and when you have a gift set, you have to include A chocolates of one kind and B chocolates of the other, right? So, but you can swap them. So you can have A of the first kind, B of the second, or vice versa. And then you have X chocolates of the first kind, and then B chocolate, or you have Y chocolates of the second kind. And the question is, how many gift sets can you make? Obviously, what you should do here is just greedily take whichever you have more of and make that gift set A. Now, that would work, and that would give you the right answer. The problem is that would be too slow, because you might make about 10 to the 9th gift sets per test case. So it's going to be not good enough. So you have to speed it up using some math. And the key observation here is what's going to happen is you're going to take a bunch of gift sets of of the same group. So you're going to either like take 5 red a bunch of times, and then after that you're going to alternate red, blue, red, blue, red, blue. Yeah, so in this case, you start alternating right away because the difference here is less than 3. But basically, when the difference is more than 3, you just repeatedly take 5 from the biggest and 2 from the smallest. There are 2 times you might run out, 2 times you might need to stop. The first time you might need to stop is if the difference becomes less than 3. The second time is if one of these runs out of candies, right? So really it'll always be the smaller one, because the smaller one's going to stay smaller. But this you could take at most 5 groups from. Even if y is enormous, you can take at most 5 groups because you're bounded by x over 2. Yeah. So that's the general idea there. You have to keep in mind after you do that, then you're going to continue alternating. So once you're alternating, you can just case that out. But basically, you remove 7 from both of them each time. And then you have to work out at the very end. You might have enough to take from one of them, but not to take from both. right? So you have to case that one out at the end. So, but basically it's just some if statements and a little bit of math, and shouldn't really be too bad. I didn't do it just because I ran out of time and I was too slow. But okay, yeah, that's all. So that's Codeforces round 725. Thank you for watching, and have a great day. Hope you did well if it was rated for you. I had some fun, even though I didn't finish coding up all the problems. I got to read all of them and solve all of them mentally, at least. Okay, yep, that's all. Have a great day. Goodbye.